This meeting is being recorded.
Okay, so last time we have discussed about the uh, design of universal gates such as AND or NAND NOR, right, using CMOS. So now in this lecture we are going to discuss about the implementation of different Boolean equations using CMOS. Okay, again we will discuss some 2-3 Boolean equations. We will implement that using CMOS. Also we will go for its stick diagram representation. Okay, so that part we will cover in this lecture. So let me share the screen. Okay, screen is visible.
Yes, sir.
Okay, now you have aware of what actually uh, CMOS is, right, and how to uh, represent a particular Boolean equation in terms of CMOS logic. Okay, so first we will go for this equation: y is equal to a plus b bracket dot c bar, the whole bar. Okay, so now this equation we will implement, right, using CMOS, and also we will draw its stick diagram representation also. Okay, now again the same story for this equation. I will repeat it for you. Okay, and from next time we will directly go for CMOS representation. So it is a PMOS, right? CMOS is made up of PMOS and NMOS, right? So this is VDD. Here actually you are taking the output. This is NMOS. Okay, and here are the inputs. And of course ground. So this is the pull up network, right? This PMOS will be pull up network, and this is the pull down network. Okay, pull up network and pull down network. Now we have to implement this equation using or we have to implement this Boolean equation in terms of CMOS logic design, right? Now how to proceed with? So all of you know I have uh, we have already discussed one rule, okay, for how to convert the dot products and how to convert the add products in case of PMOS and NMOS, right? So this is PMOS and this is NMOS. So how to convert the dot product in case of PMOS? So you have to connect that PMOS in parallel, and for add product it is series, and exactly reverse is the case with the NMOS. For NMOS, dot has to be connected in series and plus has to be connected in parallel. Okay, so this is very important rule. Okay, we are using for everywhere, so you have to remember this. Okay, from next time we will not write this, we will directly implement. Okay, now we will start to implement this. So now first thing, A plus B. First we will go for this PMOS implementation, that is pull up network. So in case of PMOS, this plus it is represented by series, right? So let us start representation. So this one is A, right? This plus is nothing but series. So this one is a B. Okay. Now this is A and this is B. So it is A, it is B. Okay. This is A and B. Now dot C. That means what? Now to this C is as it is dot. So this C is in parallel, right? So you have to connect this C in a parallel fashion. It is C. And of course, this is connected to the VDD. Okay. We have now completed with this uh, pull up network. This is a pull up network part. Now we will go for the pull down network. Okay. Again, from in between PMOS and NMOS, we are taking the output. So it is your output. Now, how to implement this? So in case of NMOS, this plus product has to be parallel. That means this A and B is parallel, right? This A and B we have to implement it parallel. So let us do this. This is B, this is A, and this is B. Okay. And now this dot C, but dot in case of NMOS, we have to connect in series. So to this C will be in a series connection. And here is a ground. C. Clear? Now this is the pull down network and this is the pull up network. Fine. Now we have to draw the stick diagram for this. Okay. We have to draw the stick diagram for this. Okay. How to do this? So first we have to represent a ground and VDD lines like this. Then by which color we are representing the P diffusion? P diffusion, obviously yellow. It is P diffusion, right? Then by which color we are representing the N diffusion? Green color. It is N diffusion. Of course, this is VDD and it is ground. Okay. Now ABC, right? ABC. So as we have a three inputs, we have to draw A, this is B, this is C, right? It is A, B, and C. Now we have to start making the connection. Okay. we have to start making the connection. So first here, for our understanding, we will mark the source and drain terminals. So it is source, it is also source, it is drain of A, again it is source of B, and it is drain of B. Obviously it is drain of C. Then, but obvious we are taking output from drain, so this will be a drain, this will be a source, again this will be a drain, and this will be a source. Okay, we have to mark this terminal so that for our understanding, and it will become easy to draw stick diagram. Okay, from this marking. So now what we have to do, we have to mark here also, so that we will there will not be any confusion. So source of A and C, it is connected. So I will consider this as a source of A and this as a source of C. So but obvious it will be a drain of A, it is a drain of C. Okay, now we have to connect this source of A, we have connected with the VDD, and also source of C, we have to connect with the VDD that we have connected. Now we have finished with this. Now where we are taking output, so output we have connected from the drain of B and drain of C. So it is drain of C, so we will make the drain here common. This is drain of B, and obviously it is source of A. So the source of A and drain of A is common, so it is common. And from this place, drain of B and drain of C, we are taking the output. Okay, it is output. Now we have finished with the pull up network part. Now we have to come to the pull down network. Okay, now in case of pull down, now as you know, this is a B and C, this is fixed one. Okay, now as you know, what we have to do, this pull down network, now the drain of A and drain of B, we have to connect the output. Okay, so now we will mark here drain of A, because we have to make that common. Drain of B, it is source of B and it is source of A, and from this terminal we have to take the output like this. That means now we have finished with this connection. Now source of A and source of B, we have to connect to the drain of C. So if you consider this C, so we will consider this as a drain of C, and this is source of C. So this both source of A, this one, and the source of B, that means this one, it is connected to the drain of C. So source of B, it is already connected. So we have to simply connect this connection. Now what remain? We have to connect this source of C to the ground. So it is source of C, we have to connect to the ground. Clear with this? How to draw a CMOS logic, then how to uh, draw its stick diagram representation. So this is a stick diagram representation. Okay. This is stick diagram representation. Clear with this? हे समजलंय का सगळ्यांना?
Yes, sir.
ओके. Now we will go for some complex design now. Okay. Now we will try to design some complex equation. Okay. How to do that? Now first again, I will not draw this CMOS connections and this rule. You have to remember this rule. See, this rule you have to remember. For PMOS, in case of dot, it has to be connected in parallel, and in case of series, it has to be connected in series. And reverse is the case with the NMOS. In case of NMOS, this dot has to be connected in series, and the addition has to be connected in parallel. Okay, so you have to remember this rule. This is very important. Okay, and this diagram also PMOS NMOS. So it is representation of CMOS. This combinedly forms the CMOS, right? It combinedly forms the CMOS. Okay, so this PMOS forms the pull-up network, this part, and this NMOS forms the pull-down network. Okay, so you have to remember this part. This is very important. Now, next we will go for a new equation, a little bit complex equation. Y is equal to a plus b bracket multiplied by c plus d plus e whole bar. Now this equation we will implement using CMOS logic, right? So again, for the last time, I will write here rule in case of dot and in case of plus and in case of PMOS and in case of NMOS. It is parallelly connected. It is series. In case of NMOS, exactly reverse is the case, right? Now we will start with the CMOS representation. Okay, first we have to go for a pull-up network, right, which is of PMOS. So first we have to go for a pull-up network which is of PMOS. So the add product should be implemented in series fashion. So this A and B will be in series. This is A, draw this. This is B. Okay, fine. Dot means what? The rest of this term it is in parallel to the this A and B. So again, in case of PMOS, plus has to be implemented in series, and this entire term it is in parallel with this A plus B. So you have to draw like this. This is C, this is D, and this is E. Okay, this is C, this is D, and this is E. Now we have finished with this pull up network part. So here we are taking the output. Now we will go for pull down network, that means of NMOS, right? So always remember this PMOS forms the pull up network and this NMOS forms the pull down network, right? So this I will write here, PMOS forms the pull up network and this NMOS forms the pull down network. Okay, so you have to remember this. Now we have to go for the pull down network. Okay, now how to go with this pull down network? Can anyone?
Sir, can you repeat the question?
For see, now this is we have implemented a pull up network, that means with the PMOS, right? Now we have to go for pull down network, that means of NMOS. Now how to implement this equation, right, using NMOS, that means how to form the pull down network of this.
Sir,
So
AB parallel,
right, so plus
BD
A plus
also
D,
parallel.
it is in parallel with each other. So first we will draw this. This is B, this is A, and this dot. So in case of NMOS, this dot has to be in series. That means for the next part, we have to connect to series with this, right? And again for plus, it is parallel. That means what? The C, D, and E, these all are parallel with each other, right? So we will draw this. Let me draw this. So this is a E, this is D, and this is C, right? So this form the exact representation of this Boolean equation. So this is a pull up network and this is a pull down network, right, of this equation. Clear with this? Now we have to go for its stick diagram representation. We have to go for its stick diagram representation. Stick diagram representation. Now for stick diagram, first we have to draw a VDD, right, and ground line. Then the P type diffusion, it is represented by yellow color, so this is p diffusion. And n type diffusion, it is represented by green color, so it is n diffusion. And the inputs we are representing using red color. So how many inputs we have? 1 2 3 4 5, a b c d e. So you have to represent the 5 lines. This is 1 2 3, then 4 and 5. Now see here, as I have to make these connections, right? I have to make these connections. Again, I will mark this. Okay. So this is a source. This is a source. This is drain. This is also drain. It is again source of B. It is drain. It is again source. It is drain, source, drain. Similarly, here also it is drain, it is drain, it is source, it is source. This all are source terminals and this all are drain terminal. Clear? So we have marked this. Now we have to start with the connections. Okay. But to have the simplicity and to get the proper stick diagram, what I will write, instead of taking this A, B, C, D, E sequentially, I will, I will little bit take this one as a C, this one as a D, this one as a E. See, you can change the sequence, no problem. This one as a B and this one as a A, right? See, why I have made this change? Because we have to connect this stick diagram and we have to take the common terminals together, right? To motto behind changing this is we have to make the common, or we have to take, or we have to consider the common terminals together in case of stick diagram, and that's why we are doing this. Okay. See, you have, while drawing the stick diagram, there is no any hard and fast rule. Okay. You can go for, you can go for a trial and error method. A single circuit may have two different stick diagram representation. It is possible. It is possible. It is not the case that whatever I have drawn, it is only the stick diagram for this. No, a single design can have multiple possible solution of stick diagram representation. It is possible. Okay. So you can uh, go for the optimum solution. Clear? Now I will mark the terminal here also. I will consider this is as a source. This is drain. This is source. This is drain. For E, it is also source. It is drain. Right? For B, now it will be a drain. It will be a source, because see, for this B and E, the drain has to made common and we have to go for a output. That's why the drain of E and drain of B I have taken on the same line. Okay. This is a drain of A and it is a source of A. Now we will go for a connection. Right. First, now the source of A and source of C, we have to connect to the VDD. Right. So where is source of A? This is source of A. We have to connect this to the VDD. We have connected. And source of C also we have to connect to the VDD. So it is source of C. We have to connect to the VDD. Okay, now we have completed this part. Now the drain of A and source of B it is common. Let us check drain of A and source of B it is common. So need not to go for any connection. Now drain of B and drain of E, we have to take the output. So this is a drain of B and this is a drain of A, and from here we have to take the output. So here we have taken the output. Fine. Now this part is also over. Now we have to go for this middle connections. Okay. So check whether these middle connections are appropriate. So this drain of C, okay, and source of D, it is a common, so it is a common. Drain of D, this is a drain of D, and source of E, this is a source of E, it is also common. So these both terminals are on the same line, so we need not to connect these two terminals. Okay, now coming to the pull down network part. Now this part we have to connect this part. Okay, we have to connect this part, but before, again we have to mark the terminals. So it is a sorry, it is a source, it is drain, again it is drain, it is source. Why have chosen this as a drain? Because see, output where we have to connect this. So this drain of C and drain of D we have to make common. So already I have made this drain on a same line so that we need not to connect this separately. Now this is a source of E, this is drain of E. Why I have taken this? Because see, the source of E, right, and the source of D we have to connect to the ground. So simply here we can take the ground connection. That's why I have made this source terminal also common. Okay, in case of B, this will be a source, this will be a drain, and again this will be a drain, and this will be a source. Now we have to go with the connection. Now first, the drain of A and drain of B, we have to connect to the output. Where is drain of A? Here it is drain of A. Here it is drain of B. So we have to connect this to the output, right? Now we have finished with this connection. Now the source of A and source of B, we have to connect to the drain of C, D and E. Where is the source of A? This is the source of A. Where is the source of B? This is source of B. And where you have to connect? You have to connect this to the, you have to connect this to the drain of E and CD. So drain of CD we are making here common, right? So we have to connect this source of B. Here it is source of A. It is already connected to the drain of E, and we have to connect it to the both drain of C and D. So these are the drain of C and D. Now what remain? So we have to connect now the source of C, source of D, and source of E to the ground. So where is source of C? Here it is source of C. Connect this to the ground. Okay, we have connected. Now what remains? Source of D and E also we have to connect to the ground. Where is the source of D and E? Here. So this terminal also we have to connect to the ground, right? And this is your full and final stick diagram, right? This is your full and final stick diagram representation. Understood, everyone?
Yes, sir.
Okay. So for this lecture, we will stop here. In next lecture, again, we will continue with one more Boolean equation and its CMOS representation and also its stick diagram representation. And then we will start with the new bit. Okay.